So now I will discuss the Maxwell equations integral form. Obviously these are the integral forms. In last lecture I will discuss about the differential form of the Maxwell equation, but these four are the integral forms. Okay, what are the forms? First one is, let me write it. First one is that surface integral of E dot dA is essentially the electrical flux. This is the Gauss law. Second one is surface integral of B dot dA is 0. Okay. Third one is line integral, closed line integral of electric field dot dl is actually d phi b. I mistakenly write that d phi e, but it is actually d phi b, it should be d phi b, and b dot dl is actually mu naught I plus mu naught epsilon naught d phi e dt. So there are 4 laws. Okay. Okay, let me write the names as well. These two are the Gauss law, this one and this one for electric field, and this one for magnetic field. This is the Faraday's law, and this one is the Maxwell, or not Maxwell, Ampere's Maxwell law. Okay. Okay, now the significance. The first one is saying that if there is a electric field and there is a the surface integral of that electric field, that means the electric flux. Means let us say if we consider a sphere, here is a point charge q, then electric field will be like this, electric field will present like this. Let me take any surface area like this, and this surface area is, this is the dA, okay, and this theta. Then we can write what will be the flux. Flux means the amount of electric field is emitting from that surface, this surface of this sphere, that is the surface integral, right, and that will be essentially E dot dA, as I discussed before. This is for small surface ds. Now if we integrate for all surface, then it will be the total flux. So essentially it is the phi E, the total flux. So clearly if there is a non-zero charge, then there will be a electric flux. If E is 0, electric field is 0, then there is a non-zero charge. Actually this E is also the uniform. If it is a isotropic space, then it will not vacuum only. If it is an isotropic space, then also this will be the uniform, and that we can, in that case we can take out the E from that integration, like we can write it E dA cos theta, and then E, then dA cos theta. We have already studied the Gauss law, right? From Gauss law we can evaluate this value. So this is the electric flux, right? So it is clear that if there is a point electrical charge q, then there will be a non-zero electric flux. If q is 0, that means there is a no charge, then that phi E will be also 0, electric field is 0. So this is the first law. The second law, B dot dA is always 0. It means that we can't put a single magnetic pole inside a sphere, or we can't create it. We have no idea about any magnetic monopole. We know only the magnetic dipole. Okay, we are very much aware of the point charge. Point charge means a electrical monopole. If there is a 2 electrical charge, then that is a electrical dipole. So we are know that the electrical dipole moment, everything electrical monopole is also well known and electrical dipole is also well known, but we are only aware of the magnetic dipole, which we are very much familiar with the magnets, right? And in each and every magnet there is a two pole, north pole and south pole. If we divided any magnet, then also there will be two pole, north south north south. We can't make, if we make infinite small magnet, then also there will be a small there will be a north pole, there will be a south pole. We can't make a magnetic monopole. So that is totally, it may be that in future we can have of the magnetic monopole as well. In that case we have to revise our law, but as per we know that there is no magnetic monopole. So essentially if there is no magnetic monopole, then there is no chances to have any magnetic flux. Okay, here we can have magnetic flux if we have the magnetic dipole only, otherwise. So this is the first law. Okay, that B dot dA is 0. Now the Faraday's law. Okay, so this is the Faraday's law. What is the meaning of the Faraday's law? That if there is a magnetic flux, if we consider any magnetic field, let's say if there is a magnetic field, this is N, this is S, then there will be a magnetic field. Okay, and also there will be a magnetic flux. If let's say if we changing the magnetic field with time, then there will be a magnetic flux. So if there is a magnetic phi b is the magnetic flux, so if we changing with time, the magnetic field is changing with time, then the phi b will also change with the time. So there will be a change in magnetic flux with respect to time. So that is this. In that case, if we change that magnetic flux is changed with respect to time, if we put a wire like this, then there will be a current. Okay, so there will be a current I. So it means that if there is a changing time, the magnetic field which is changing with respect to time, that can create a electric field. The outcome of the Faraday's law is that if there is a magnetic flux which is changing with time, then an electric field will be generated and we can have the electric current, as we can see here. Okay, this is the impact of the Faraday's law. And the fourth one, the Ampere's-Maxwell law. As we discussed before, the impact of these two laws, that magnetic field can be produced if current flows through a conductor or electric field varies with the time in a region. Okay, so what is the main output of this four Maxwell's law? Are that if there is a magnetic field which is changing with respect to time, that can create an electric field. If there is an electric field which is also changing with respect to time, that can create a magnetic field. Okay, so if we write that electric field can generate a magnetic field if electric field varies with respect to time, and this magnetic field can generate electric field if that magnetic field also varies with respect to time. Okay, so it's a loop. Okay, that electric field can generate magnetic field, again that can generate electric field, and it goes on. Essentially, in this fashion, electromagnetic waves generated. So what is the definition of electromagnetic waves? So as I discussed before, that electromagnetic waves essentially consist two parts, electric and magnetic. That means that there are two fields, electric fields and magnetic fields. When these two fields make a propagating wave, then that is called the electromagnetic waves. Let me write the proper definition of the electromagnetic waves. definition. Okay, so this is when varying electric field, which is E, and magnetic field, which is B, exist in a place, then these varying fields spread out in all direction like a wave, which is called electromagnetic wave or electromagnetic radiation, that's same thing. Okay, so why it is wave? Because it's actually propagates. Okay, as we are familiar with the sound wave or the mechanical waves, these are all wave because wave means there is no mass, the energy is propagating in the vacuum or any using the medium, then that is the wave. So here is the electromagnetic wave essentially can move through a vacuum if there is a varying electric field or the varying the magnetic field. Okay, so analyzing that Maxwell equations, we have already shown that electric field and the magnetic field both are perpendicular to each other, and also that wave generated due to these fields propagate through a perpendicular direction, which is both perpendicular to the electric field and the magnetic field. We can identify using the wave vector, k vector. Okay, so from there we can from that we can we have already drawn that. Let me draw again. This is our, let's say, direction of propagation. I am not repeating the calculation. Here it is the electric field is operating that way, and here it is the B. Let me erase that part. Okay, so the magnetic field will be so electromagnetic wave will be like this, So here this is the electric field. Okay, this is a snapshot of a time also. I've also said that. So from here we can see that electric field is varying with respect to time. After some time it is like this. If we only focus on the electric field, it's like this, then it will be like this. As we know, all the waves is changing with respect to time. So electric field, which is along this direction, that will change with respect to time, which creates the magnetic field in a perpendicular direction. How? In which direction? In this direction. Oh no, let me take another color. Okay, so B is playing in this direction. Now B is changing with respect to time as well. So now this magnetic field also create the electric field in the perpendicular direction. So in this fashion it will propagate, and the direction of propagation is both perpendicular to both that electric field and the magnetic field. Okay, so this is the electromagnetic wave. Okay, let me summarize my today's class. Okay, first we have in today's class we discussed about Ampere's circuital law, then we basically for path or line integral. Then we discussed displacement current, and from that displacement current we discuss about Ampere Maxwell law. Then we discussed four Maxwell integral form of the Maxwell equation. Integral form of the Maxwell equations, and then we discuss the electromagnetic waves, and before that okay, then we discuss electromagnetic waves. Okay, so in today's class we discuss that. In next class we will discuss about some radiation pressure, and that also some the energy density of when electromagnetic waves propagates, then there is a energy density. Okay, so we have to calculate that energy density, and also we will discuss radiation pressure, and then we will discuss about the various range of electromagnetic radiation. As I in previous class, in first lecture also, I have just written down the various electromagnetic waves like that, starting from the cosmic ray, then gamma ray, then X-ray, and then also ultraviolet, then visible, then IR, and these things. So I will discuss in detail in next class that also the spectrum of the electromagnetic waves. And first we will discuss the energy density, then Poynting vector. Let me write. In next class we will discuss energy density, Poynting vector, radiation pressure, and spectrum of the, I don't know it will be covered in one lecture or not, I will try, electromagnetic waves. Okay, so let me stop here. We will meet in next class again. Thank you.